All right. So the standard normal is restrictive because it has mean 0 and variance 1. The general normal distribution has an arbitrary mean and arbitrary variance. So it has a mean different from 0 and a variance that's different from 1. The probability curve for the general normal is 1 over the square root of 2 pi times sigma squared times the exponential of 1 minus 1/2 x minus the mean squared divided by sigma, all this quantity squared. And then, I don't know why I have dx there. And this goes from minus infinity to infinity. So in this, so this is the general bell curve. The expectation of a general normal random variable, the mean value is equal to mu of x. So that's the interpretation of this parameter here. The variance of x, so that the square deviation from the mean turns out to be sigma x squared. So that's what this parameter measures. And then the standard deviation is the square root of the variance. So when you think of graphing a general normal random variable, it has mean mu of x, and then mu of x plus the standard deviation, mu of x minus the standard deviation. So the area under this curve is 67%. So if you go mean minus the standard deviation, mean plus the standard deviation, 2/3 of the probability is between those points. Okay. So again, that gives a specific interpretation to the standard deviation. When you have a bell-shaped distribution, then you have this kind of relationship. Okay. So important facts about the general normal, centered at mu of x. It's symmetric about the mean. And then, again, we have these probability results. The probability that x is plus and minus 1 standard deviation is 2/3. The probability that x is between plus and minus 2 standard deviations from the mean is 95%. And the probability that the normal is between plus and minus 3 standard deviations is 99%. Okay. We also have this result that the quantile function for a general normal, and you'll be asked to prove this in the homework assignment, the quantile function for a general normal is equal to the mean plus the standard deviation times the quantile of a standard normal. Okay? So what this result here tells us that if you want to look at some particular probability value here, say if this is 0.05, and this is mu of x here, the quantile function q of alpha is equal to the mean plus the standard deviation times the quantile function of a standard normal. And z alpha is equal to phi inverse alpha. So this is the alpha quantile standard normal. Okay. So we'll derive this result later on. But again, quantile is going to be so important for us, particularly in determining risk. It's nice that we have this simple formula for determining the quantile of a normal. Depends upon the mean, the standard deviation, and the quantile of a standard normal by itself. So obviously, if the mean stays the same but the standard deviation increases, then the quantile gets bigger. Or if the standard deviation stays the same but the mean gets bigger, the quantile gets smaller. The quantile gets bigger. So that'll be a useful result. All right, so obviously the standard normal is a special case of the general normal. Now, one of the things about the normal distribution is once you know the mean and the variance, then you can draw the probability curve. Everything you need to know about the normal distribution is governed by 2 parameters, the mean and the standard deviation. So once I have those 2 parameters, then I can do all probability calculations that I need to do. So that's again, that's a nice feature of the distribution. Just depends upon 2 numbers. All right. So, so to do probability calculations, we have to be able to calculate area under the general normal curve. So if we're working in Excel, there's a function called norm dist. So before we had the function norm s dist, that was for the standard normal. Now for the general normal, we just have norm dist. The s disappears. And this function takes we have 4 arguments, x, mu of x, sigma x, and cumulative. So we're calculating the normal distribution at a particular point We give it the mean, the standard deviation. And then cumulative is a logical variable. If cumulative is equal to true, then this function computes the CDF. If the cumulative variable is equal to false, then this function computes the height of the normal curve. That's just the way that it works. And if you want to compute the quantile function of the general normal, there's a function called norm INV. And it takes a probability value, a mean, and a standard deviation. And this computes the normal quantile, which would be computed this way. And then similarly in R, if we wanted to do computations with the normal distribution, there are 4 functions for doing computations with a distribution. So if we want to simulate data from a normal distribution, sort of simulate pseudo data, there's a function called rnorm. So R means random number generation. This is from the normal distribution. How many random variables do we want? How many random observations do we want? And then the mean and the standard deviation. The CDF, again, is p-norm. And then the quantiles is q-norm. And then the density is d-norm. So we can do these kinds of computations. All right.